distinguish between chaotic and complex dynamics. More concretely, we expect chaotic systems to be more complex in colloquial words, or to be able to produce more complexity than simple systems. Now, given these completely intuitive, almost meaningless statements, it is interesting to see that quantum complexity and quantum chaos are by now two pretty sophisticated and evolved fields, and they have actually very mild breeds between them. And so, for example, there is we all know a famous conjecture in quantum chaos, which states the universality of spectral statistics in chaotic theories. So this is sometimes comes under the name of Boygas-Giannoni-Smith conjecture. Aspects of this conjecture have been brought to our field in the form of the spectral form factor, to be defined later, and this has indeed, this has been pretty much studied in recent years in the context of black holes. Yet there is no relation between this famous, maybe the most famous quantum chaology and the field of quantum complexity. Another fundamental corner of quantum chaos is that of Lyapunov exponents and semi-classical physics. And in this direction, for example, and we all know that there are actually important bridges between this corner and the corner that I just mentioned of random matrices. But and in this direction, there has been several recent movements building connections also to quantum complexity, namely through operator size, Nielsen complexity, Kirillov complexity, and also developing relations between chaos and geometry. And to end with these motivations, from a non-dynamical, also from a non-dynamical perspective, we were also motivated to understand the complexity of Einstein states in a precise manner, and probably to connect with recent work on Nielsen complexity by Vijay, Arjun, and collaborators. So this is, of course, a vast and challenging territory, and today we are going to fill just the first part. So namely, we are going to describe a precise relation between the quantum chaos conjecture, the spectral form factor, and the quantum complexity, and apply it to black hole physics. So the last set of motivations come from quantum gravity. In particular, we are interested in the conjecture long-time complexity dynamics for chaotic systems and black holes, and also in the so-called holographic complexity proposals. Relatedly, we were motivated in the relations between complexity and general relativity, whether in the form of so-called path integral complexity or Nielsen complexity geometry. In this direction, we will concentrate today just on the long-time dynamics of complexity, and indeed we will refine such kind of conjectures on such behavior. Let me say that also that although we are not going to focus on it today, our measure will turn out to be related to precise geometric avatars, and we hope that this will pave the way to understand other points on these conjectures as well, but we will not talk about them today. So having laid out the motivations, let me go to the plan of the talk. We will start with the definition, and then we will explain two computational tools or two computational methods which are convenient in different complementary situations. So we will then apply in several examples, and to have some intuition, some concrete intuition, we will start by describing some models that can be treated fully analytically. And then we will move to the core of the talk and describe several examples related to black holes, such as the Schwarzian theory, random matrices, and the SAT-Z-J-Kita-F model. We will end up with a summary and a discussion. Okay, so let's move to the definition. For the ones that maybe are not so much interested in the quantum complexity per se, please bear with me. Then we are going to study it completely explicitly in black hole-like systems. So it goes as follows. Suppose we start with an initial state here, psi 0, and allow it to spread through time evolution. The question we want to ask is how can we characterize? So the question we want to ask is how can we store this state? And we can store it by store the amplitudes in a certain basis. And we would want to say that the complexity in that basis is more or less the number of amplitudes that I need to store in order to store the state. So to be a little bit more precise and mathematical, for a given but arbitrary basis B, we can define a notion of a spread by means of the following formula. In this formula, the coefficients Cn are strictly growing as a function of n. A possibility would be, for example, just Cn equal to n, okay? But it won't matter the definition for what I'm going to say now. An alternative, the intuition for this quantity is just that as the time evolution proceeds, the spread of the wave function becomes bigger and bigger, and this notion of a spread will be bigger and bigger until it saturates to the maximal value when the state is spread over all basis vectors. So an alternative definition, which we're also going to use, is just the exponential of the entropy of the probability distribution in the given basis. And here we are not going to make any distinction between both. We will study both and consider both. What is important now is that, again, we face here an ambiguity. No? The question is exactly what basis should we use to compute this quantity. In this sense, let me say that there have been, not in the context of state complexity, but in the context of operator complexity, there have been proposals that actually can all of them be framed in this way, just by defining some notion of a spread in the operator basis and compute it. The difference between them is just the basis that was chosen. So we see here the importance of the ambiguity. So
I think that we have a question from Elliot.
Yeah.
Can you hear me?
Yes.
Yeah. Okay. So I mean, one thing that strikes me about this definition is if you were considering like the quantum computing setup, and suppose we picked our basis to be the computational basis.
Just one comment, sorry. I still didn't finish with the definition because maybe this is not the definition. This is just the context for the definition. Now I'm going to define it. If you want to wait 1 minute, because maybe it answers your question.
Okay. But my point was just you could have a state with no entanglement, and it would still be very complex according to this definition.
No, because this definition it's completely tied to the initial state that you take. It will always be if your entangled state is the initial state, it will have zero complexity just by definition. Let's say. So you would need this definition of complexity is going to be tied to an initial state and a quantum evolution.
Yeah, but
he's just defined spread so far, right?
I have just defined a spread so far. Yeah.
Why don't we let him finish and then we can bug him about it.
Yeah.
Okay.
So what we propose here is that to solve this ambiguity, and in Kolmogorov spirit, we define the complexity as the minimum of this spread over all choices of bases. Now, let me just remark that the relation of this definition, which is still a particular definition of quantum complexity, to the usual definitions of quantum complexity done in the quantum complexity literature, is still to be developed. And there are points that for sure go in line to the questions you have. But let me just say that at least from a intuitive perspective and from a physics perspective, it is an unambiguous definition that well, that we are going to see why it is interesting. But it is just tied to initial state and a quantum evolution, and then we just ask the question. So we can define a notion of a spread for every basis, and then we just say, okay, complexity should be the minimum of all those spreads, because in that minimum I will let's say do the minimum effort in order to store the state. That's a little bit the intuition.
Can you say what stops me from choosing the basis that begins with the pure state you're in at any particular time?
Yeah. So so this is actually this equation. This is explained in the article, and excuse this is a little bit abuse of language in the talk, but it is not a minimization at each time. So you have to choose one basis at the initial time, and then it has to minimize through all times. So of course, what I'm saying is that of course you can choose at every time, you can choose that vector at that time, but that will not be minimal for different times. So this is a non-local definition. Let me go to the next slide and you see that. So okay, so given well, let me say that this sort of definitions based on optimization over a space of possibilities has appeared many times in physics. So let me just say that I'm going to define the minimization a little bit more precisely, and it will solve your question. It is perfectly I want to say that your question makes complete sense, and we are going to solve it in a moment. So before that, let me say that these sort of definitions based on optimizations kind of sound nice sometimes, and they have appeared in many places in physics and mathematics, but it is typically the case that they are of a small practical use, since they cannot be solved in explicit examples. And this is the interesting thing is that this is not going to be the case here. Here we can solve such minimization precisely, and so we are going to do it in a moment. So to see what is that basis which solves the minimization, notice that given the initial state and a unitary evolution, there is a canonical basis that we can construct out of it. Basically, we just start with initial state and we construct this application of the Hamiltonian n times. We construct these states, and then we can perform a Gram-Schmidt procedure on that basis and construct an orthonormal basis. Okay. This gives, by construction, the orthonormal basis for the part of the Hilbert space that is explored by time evolution. This part of the Hilbert space might not be the full Hilbert space, but that is not really important for us. And also, for chaotic systems, it will be the full basis. Now, what we are really going to define, the question was completely correct. If we define just minimization at single time, this makes no sense because I can always take the state at a given time. But of course, then that doesn't define a basis for all times in which I'm going to store, let's say, the full protocol at every time with a single basis. So what we are going to do is to basically to come up with a non-local definition of minimization, in which we define the following string of derivatives at time equal to 0 of the spread. So this infinite string, and we are going to minimize to do what is called as we are going to minimize over the different strings of the different strings. We say that a string is smaller than another string if the first so if they are equal until some point, and then the next entry is smaller. This in particular implies that for a finite interval of time around t equal to 0, the complexity would be strictly smaller than in the basis that minimize this string. Maybe this was not. This is better explained in the article, but I didn't want to enter in the techniques. This a little bit explains your question or not?
Are you asking me?
Yeah, yeah. If this kind of clarifies your question or not.
Oh, now I'm frozen, I guess. Can you hear me?
Yeah, I hear you.
Oh, okay. Yeah, my question was really about whether this measure is related to entanglement at all, because I don't see that. Like it's related to the spread of these coefficients, but you could have a state which is like spread over a lot of basis states and still has no entanglement. Whereas intuitively, I would think that complexity should have to do with entanglement.
We have not developed that connection. Yeah, we will. It's interesting to work it out. We are going to develop a connection of this one to quantum chaos. It's going to be very precise.
Yeah, I mean, if you're coming at this from like quantum computing, then you think of complexity as having to do with like the depth of the quantum circuit that you need to produce the state, or the number of C0 gates that you need or something, and that has to do with the entanglement in the state.
I'm not saying that this is not going to be that we. I'm just saying that we have not developed that still.
Yeah.
I mean, it's natural that if I have a spread that is if I prove, for example, that the spread is maximal in most bases, that the state is going to be highly entangled. So when I'm minimizing the spread over all bases, then what I'm proving is that if I study the spread in the bases that minimize, if I prove that spread is huge, this proves that the spread in all other bases is also huge, and therefore the state is very entangled. But we have not developed that for the moment. But of course, we expect that there is going to be a relation. So what we prove in the article is a couple of theorems and a corollary. So basically, for any basis that one chooses, this string of derivatives is smaller for the kilo basis, for the basis that arises by Gram-Schmidt orthogonalization of the different powers of the Hamiltonian in the initial state. And also, not only that, that equality only holds for the basis, for all bases that contains the kilo basis. Could be only one or could be more. Also, this implies that the spread defined by this increasing sequence and the basis is minimized near t equal to 0. This is a problem in the continuous evolution. It would be nice to extend this theorem to cover the full time evolution. But for the moment, yes, we have some theorem regarding the initial part. And in that case, the quantum complexity defined in this way is equal to the spread in the kilo basis. And to solve this issue of minimizing only over a short period of time, actually one can do the same logic, but just for discrete time evolution, which connects much more to the usual protocols in quantum computing. And here you can really prove that the spread is minimized in the kilo basis at all times. You don't need the small time assumption.
Okay.
Yeah.
This may just demonstrate I'm really at sea, but in defining in stating that one string is smaller than another, you go out some number of components, and then you start asking when are derivatives smaller. Are you making some assumption about differentiability, that the higher derivatives are generally decreasing? Or
But
because you could have it get smaller, and you could have it be smaller at third derivative, and then the fifth derivative is just wonking huge for one of.
Exactly, but that's the problem with continuous time evolution. Exactly, that if you prove that it's smaller until fifth derivative, you know that at least over an interval of time it will be smaller. What happens later, we have to there is room for improvement of the theorem. Right. I mean, to give confidence that this is kind of a sensible path is that if you do it for discrete time evolution, you don't have this problem, and then you can prove it for all times.
Markana?
Okay.
Hi, just a quick question about your definition of C, which is exponent of the entropy. So at least in information theory, that is typically the way to define, in some sense, the number of typical sequences in the sense of intro, like.
Exactly. This is just the intuition. This just comes from that intuition. Yes.
Okay, so the more, okay, I see. So the complexity is defined as, like, in some sense, the minimum number of typical sequences you have, and the bigger the number, bigger the complexity.
Exactly. The smaller number of typical sequence you need to use to store the full evolution until certain time.
All right. Okay. Thanks.
Okay. So I'm not going to explain the proof of those theorems. It is not very hard. I would lie if I say it's very hard, but I also will completely lose you if I put it here, because it's also not very simple. So it is just that. So we need to compute the complexity. We need to find this basis, this kilo basis, and so we need to find all these states, and then we need to do Gram-Schmidt procedure. And this has a solution and comes under the name of the Langsos algorithm, which is just recursion relation, which keep building new states out of the previous ones. And the protagonist in this story are these coefficients, these ANs and BNs, which are called the Langsos coefficients. This is known since long time in the condensed matter literature. Let's see. So, a moment. So these equations here, what they, I mean, so let me explain how we are going to do it, like in practice, because of course we could do it. I mean, this is a precise method, but in practice we are going to use numerical methods or analytical methods. Let me just say that these equations here imply that the Hamiltonian in the Kirillov basis is just a tridiagonal matrix. So it acts in this way. We have just the diagonal and the elements above the diagonal. So if we find these Langsos coefficients, we have the Hamiltonian, and we can compute the evolution. In the literature, this form of the Hamiltonian, which can always be found, is known as the Hessenberg form of the Hamiltonian. Okay, so actually for finite matrices, if your Hamiltonian is really a finite matrix, you can just put it into mathematical, ask for the Hessenberg form, and it will give you the Hessenberg form. So in our case, for finite system with discrete spectra, such as the SYK or matrix models, we can use these subroutines and read up the Langsos coefficients directly from this form. But this computational method does not work for infinite dimensional systems or systems with continuous spectra, as the ones we find in black holes. So we are going to derive one more general, and it is the following. So we are going to first define the survival amplitude, which is the amplitude for the states to remain unchanged as time evolves. So as we are going to assume, and this is going to be the case for black holes, we are going, but let me assume it now for explaining the method. We are going to assume that we can compute this quantity by other means. So somebody gives you this quantity. Then we can compute the moments that appear in the Taylor expansion around t = 0, and these are just the expectation values of powers of the Hamiltonian in the initial state. Now, so we have so basically, if somebody gives you the survival amplitude, then that person is giving you the moments just by taking derivatives. And now we remind the action of the Hamiltonian in the Kirillov basis was this tridiagonal action, which we can understand such action by what is known as a Markov chain. So in this Markov chain, the nodes are the Kirillov basis vectors, and the arrows correspond to possible hoppings along the chain. So basically, this is an interesting thing that at least I didn't know about when I started this, which is that every quantum mechanical evolution can be mapped to the dynamics of a one-dimensional change in this way. So let me say that. Let me repeat it again. So more concretely, in this Markov chain, the weights are the Langsos coefficients, and the Hamiltonian is the transition matrix. So we can use this perspective to compute the moments from knowledge of the Langsos coefficients, or to compute the Langsos coefficients from knowledge of the moments. I'm not going to explain it in detail. It's explained in detail in the article. It's a little bit cumbersome. It's not very simple, but it just comes by unwrapping the Markov chain, and by noticing that step by step, I always have enough information to compute the Langsos coefficients from the moments, or vice versa. For us, in what follows, basically we will give the theory under consideration. For example, the theories concerning black holes will be providing the survival amplitude. And with this survival amplitude, we will be able to compute the moments, and with the moments, we will be able to compute the Langsos coefficients, and with the Langsos coefficients, the wave function in the kilo basis. So, okay. So we have described two methods to compute the Langsos coefficients. One is very simple, it's numerical. It is just this Heisenberg form. If the matrix is finite, we just ask for the Heisenberg form. But we have also explained this other from the survival amplitude. Now, once we have the Langsos coefficients, we proceed as follows. We expand the time evolving state on the kilo basis. On this basis, the Schrödinger equation takes this explicit form, which is this one-dimensional Schrödinger equation, discrete Schrödinger equation. In this equation, the survival amplitude, in this wave function in the kilo basis, the survival amplitude is just the first amplitude in the kilo basis, and from this amplitude and the Langsos coefficients, we can compute the full wave function just algebraically. We don't need to solve any differential equation, because we input the survival amplitude, and then we just go step by step computing all the other entries. From these amplitudes, we then compute the probabilities, and from those we can compute the spread in this basis, which I remind minimizes the spread in all other bases. So this is admittedly a very involved computational process, but let me just remark what is interesting here, and maybe also at the definition level, maybe there are problems in relation to quantum complexity. But the nice thing is that otherwise totally straightforward. So before moving to specific examples and to motivate and convince to convince you all that this is a worthwhile direction, it is illuminating to apply this framework to the thermofield level state. So the thermofield level state is defined as usual. So we make the tensor product of the original Hilbert space with itself. We call one of the theories the left and the other the right. We then use the eigenstates of the original Hamiltonian to construct this state here. So these n's are the eigenstates, and they have energies En. And I construct this state here is the thermofield double. This state is invariant under the evolution by the difference between left and right Hamiltonians, but it is not invariant under the sum, or also just for simplicity is equivalent. It is not invariant under the evolution with only one Hamiltonian, say the left. So actually, well, let me say it in 1 minute. So under such evolution, I get just this equation. So basically, one obtains an analytically continued thermofield double. So basically, it's like analytically continue on the temperature. And let me say that in ADS-CFT, as we all know, the thermofield double is dual to the eternal black holes, and this evolution is expected. This is expected to describe aspects of the black hole interior. How this evolution is going to do that is still something to develop that we are not going to do today. But well, this has been the inspiration for many in recent years to study the black hole interior. So we just evolve with one Hamiltonian instead of with two, and we are going to analyze the wave function. So the interesting thing for us is that the survival amplitude in this analytically continuous thermofield double is the analytically continuous partition function. So in other words, the survival probability that is basically that everything is going to depend on is what is known as the spectral form factor in the random matrix theory. So so yeah, as I have mentioned in the motivation, this physical quantity has played a leading role in the context of quantum chaos and also in recent research of black holes. Here we see it just as the first entry of a dynamical probability distribution, namely the distribution of Kirillov probabilities associated with the evolution of the thermofield double. So also, this distribution and the associated complexity are functionals of this survival amplitude itself, and this then is a very promising avenue, which we're going to back with results. Is a very promising avenue to build a bridge between quantum complexity, quantum chaos, and quantum gravity. So, and let me say that this we haven't worked on, but it also provides a promising avenue to turn the characterization of phases of quantum matter in terms of partition functions into a classification of phases in terms of the dynamics of quantum complexity. So is there some questions here? This is kind of an important, a basic observation that is going to control yeah, all the applications. So, okay, so I was going to comment on the analytical models based on this certain symmetry groups, but I'm going to go to the black hole physics models, which are more interesting, and also just for the sake of time. So let me just go. So we are going to start with the Schwarzian theory. This theory is known to appear in the low energy limit of the Sazet-Yekitaev model, and also it appears as the boundary description of JT gravity. It is defined by the following Euclidean action in 0+1 dimensions, where F is the degree of freedom, and the brackets stand for the Schwarzian derivative, which is defined here. The coefficient C in front of the action can be thought as a central charge or as an inverse coupling, and then the semi-classical or weak coupling limit arises just by taking the large C limit. Okay. The interesting thing is that this model can be solved explicitly. In particular, the SYK partition function is this one here. From this SYK partition function, we see that this model has a continuous spectrum. So we cannot just compute the Heisenberg form, which was the first method described before for finite systems. We need to use the second method. But let me say that at least we have the partition function exactly, and which means that we have the survival amplitude and of the thermofield double exactly also. And or equivalently, we have all the exact moments, which are this one here, which can be computed in terms of a hypergeometric function. So we just take these moments, these exact moments, and from them we can numerically compute the Langsos coefficients. We can go over this kind of involved process to compute these Langsos coefficients, these ANs and BNs, in which the Hamiltonian takes this simple tridiagonal form, and we obtain this these plots here, which actually we can reproduce them analytically by assuming certain symmetry group, which I didn't describe, but it's in the article. So we can reproduce this analytically, but it brings a lot of machinery to do it. So from this form of the Langsos coefficients, we can compute the complexity, and we get these results. So complexity grows quadratically, and this is this is indeed what people expected for short times. It is not what people expected for long times. And the reason is that the system is infinite and the spectrum is continuous. So actually we expect that we are going to get a more sensible complexity when we actually deal with black holes formed by collapse, and in particular black holes that have a finite energy band and that can be described by a macrocanonical ensemble. To do that, we need to go to finite systems, and that's what we are going to do now, which is going to be a little bit more clear. So before describing the explicit results for finite systems, let me motivate a bit the models that we are going to describe. These are the random matrix and the Schwarzian models. And let me just say why and where we should trust the prediction. So basically, basic conjecture in the field of quantum chaos states that the fine-grained structure of the spectrum of quantum chaotic Hamiltonians is well approximated by the statistics of random matrices. This is sometimes known, as I mentioned before, as the Boigas-Giannoni-Smith conjecture. And then the interesting thing for us is that if this is true, given the energy time uncertainty principle, we expect that aspects of the long-time dynamics in chaotic systems will be well described by statistics of nearby eigenvalues of the Hamiltonian in the random matrix approximation. So since we seek to understand universal aspects of black holes and more general chaotic systems, it is natural to start by considering these random Hamiltonians. And we will study the three universality classes. We will study the Gaussian unitary ensemble, the Gaussian orthogonal ensemble, and the Gaussian symplectic ensemble. So the first one, the Gaussian unitary ensemble, is defined as an ensemble of Hermitian n by n matrices with Gaussian measure. Given this ensemble of finite dimensional Hamiltonians, we are going to follow the following steps, which are we are going to follow the process that we explained at the beginning, which is a little bit involved, but let me repeat it. Well, first, because we are dealing with an ensemble, we need to first take an instance of the random Hamiltonian. When we have one Hamiltonian, this is a finite matrix. We can diagonalize it and we can construct the thermofield double. Once we have the thermofield double, we can find the Hamiltonian in the Kirillov basis just by computing the Heisenberg form, and from such a form we can read the Langsos coefficients. Now, because we are in a finite system, we can just find the wave function at time t just by matrix exponentiating this Hamiltonian and reading the entries basically when applied to the initial vector. And then from the wave function we can compute the quantum state complexity. We of course are going to do this for we have to repeat this process for different values of the temperature and different values of n and different instances of the Hamiltonian. So let me start with the Langsos coefficients. How do they look for random matrices? So for finite n, these are given in these two figures here. So we notice, of course, two regimes. The ANs plateau very rapidly at 0, and the Bs slowly decay at a rate of order 1/n. So even if you see a decay, you should see really like they are plateau because they are these plots are as a function of little n divided by the full dimension of the Hilbert space, which is capital N. So in particular, this means that for any finite interval of little n, they are constant, but of course they need to decay to 0 since the system is finite, and the Langsos algorithm must halt when we produce a full basis of the Hilbert space. So in this case, we are going to produce really a full basis, and this is seen here. This is kind of a signature of chaos already, that the evolution explores the full basis. This is in here in the plot by noticing that the little n goes until capital N, which is the dimension of the Hilbert space. And let me say that similar behavior for the Bs has been found in the context of Kirillov operator complexity. in this couple of works. We can zoom, so we can analyze the transition. So we see here a very sharp linear growth, which we cannot even almost study. We can analyze that transition from the linear growth to the plateau just at infinite n, directly at infinite n. We take the leading average density of states and use the second method, again, compute the moments of the Hamiltonian and compute the Langsos coefficients. And this plot shows that the transition from linear to the plateau occurs at little n of order 1 in the large n limit. And this differs from the Kirchhoff operator complexity and suggests that the analogous transition happens at a time of order 1, which we are going to see in a moment. So
I think there's a question from the chat.
Yeah.
I think Elliot is asking if these are in TFT states.
These are what?
The question is, are these in Thermofield double states or something?
So here what we did is the following. I'm going to repeat. So we are going to consider the Gaussian unitary ensemble. We are going to draw a Hamiltonian, a explicit Hamiltonian. It's a finite. We are at finite n, which is the dimension of the Hilbert space, or the dimension of the matrix. We're going to take a explicit Hamiltonian with all the numbers. We are going to diagonalize it, and we are going we have then the eigenvectors and the eigenvalues. And with that Hamiltonian, we are going to, and with those eigenvectors, we can construct the thermofield double. It is just the sum of, we can construct the tensor product and we can construct the thermofield double. Okay, it is going to be an instant of the thermofield double for a particular matrix drawn from the Gaussian unitary ensemble. Once we have that, we can evolve that state with the Hamiltonian in one of the theories, which is the one we started with, but now tensor product with the identity in the duplicated Hilbert space. So we are going to exactly reproduce the situation that is interesting for black hole physics in order to explore the interior and to explore complexity at long times. Did this answer your question?
Yeah, thank you. Sorry, I missed that the first time.
So, so now using these Langsos coefficients that we have computed, we can compute the probabilities and the quantum complexity in the way that we did it, and we find these plots here. Notice just first that these plots are like the x-axis and the y-axis are both, so the complexity and time are both normalized by the dimension of the Hilbert space. So yeah, that's why they are both of order 1, but you should see that all these scales, both in the complexity and both in the times, are exponentially big in the size, exponentially big in the entropy, so are proportional to the size of the Hilbert space as we expect. So let me say that in this figure, you should look first to the dark hues, and this corresponds, so the dark colors, and this corresponds to the Gaussian unitary ensemble for different temperatures. So basically the darkest blue corresponds to infinite temperature, and then we go in lowering the temperature. But the ones that correspond really to this process that I have just mentioned are the ones that show this peak. So this dark with dark colors. So it is obvious that the Gaussian unitary ensemble complexity displays 4 regimes. So we have a ramp for exponentially long times, a linear ramp, which is what now this is really what we expect from the for chaotic systems. We have and also well, in more general quantum computing considerations. So we have a ramp for exponentially long times until a peak of exponential size. Then we have a downward slope until a plateau is reached. The plateau time and the height of the plateau are also exponential in the entropy as well. Now, in this plot, we are also plotting a related ensemble with light hues. So for every temperature, we have here another lighter color, and this corresponds. This ensemble corresponds to do the same that we have done, but just picking eigenvalues from the Wigner semicircle law and running the program again. So the difference here is that these two ensembles have the same density of states by construction, but in the second one, we have basically erased by hand, is a way to erase the universal correlations that appear in random matrices. So when we do that, when we erase those correlations, we see qualitatively similar behavior, but the complexity dynamics mix the peak and the slope. And we are going to explain this in a moment. Are there some questions about this plot? Okay.
So far you're just showing plots from like GUE and GOE. You haven't done any plots for SYK yet, correct?
No, correct. Yeah, this is just GUE. I haven't done GOE and GSE either. This is just GUE. This is GUE.
Yeah. Are you going to have any for SYK in particular?
Yes.
Okay.
So this behavior reminds us to the behavior of the spectrum form factor in random matrix theory. So from the present perspective, let me remind again that the spectrum form factor is just the first entry of the probability distribution in the kilo basis. So it's the first entry in an exponentially large probability distribution. This spectral form factor is known to show 4 regimes as well: a slope, a dip, a ramp, and a plateau. In this case, it is known just by direct computation that the dip and the slope are originated in the notion of spectral rigidity in the matrix model, which I'm not going to describe here, but we can discuss later. These are the universal correlations between the eigenvalues that are not so near to each other, basically. So the way to prove this is just to notice that in this scenario, the ramp and spectral rigidity, basically they are just Fourier transform of each other. So it's very simple to prove the relations. But in the complexity case, the slope here, it's a very subtle regime that appears at much larger time scales. And that depends on all the probability entries, not just on the first one, which is related to the density correlation in a very simple manner. So how do we know that the complexity slope arises from the spectral rigidity? This is the question. So one strong hint is to consider this other ensemble with the same density of states, but with no universal correlations. This, let me say, a Wigner ensemble, in which we just draw eigenvalues from with the same density of states, but in which all correlations have been erased, because this is not really a random Hamiltonian. So when we do this for the spectral form factor, we get this plot here, the one that says uncorrelated, the light blue, in which we see no ramp and no dip. Okay, and the same happens. For the complexity. So let me say, just for completeness, that we can also that this doesn't depend on the definition of the particular definition of complexity, and these 4 regimes can be also found in the alternative definitions. For example, the exponential of the entropy, and also we studied the variance, and in those cases we have verified as well that the slope that also appears here in those cases, it disappears when we erase the universal correlations that are typical of quantum chaotic systems. So what is this complexity slope? So to better understand it, we are going to take snapshots of the wave function of this thermofield level wave function for different times. So again, here the spectral form factor would be the n equal to 0. So here you have these plots. Each of them, they have the probability distribution for every n from 1 to capital N, which is the dimension of the Hilbert space. The first one is the spectral form factor, but we have all these others which begin to be populated as time evolves. We see that the wave function of the thermofield level behaves as a coherent. I mean, the important thing here is that the wave function behaves as a coherent subwave. It leaves a relatively small tail of probability behind as time evolves. So in particular, then the front of the subwave overshoots the plateau and arrives really to the end, like to the farthest states in the Hilbert space in relation to the initial state. It overshoots that, and then it goes until those farthest state, and then because the Hilbert space has finite dimension, it bounces back, and then it plateaus. And this overshoot of this coherence, which is controlled by spectral rigidity, and that produce this overshoot, is the origin of the slope in the complexity. To deepen more on the slope, we are going to know are there some questions about these snapshots or this plot? So to deepen more on the origin of the slope, we are going to notice something. So it is well known in the literature of random matrices and quantum chaos that the spectral form factor that we described rapidly before actually differentiates between the three universality classes: the Gaussian unitary ensemble, the Gaussian orthogonal ensemble, and the Gaussian symplectic ensemble. This is explained in detail in this nice book here, from where I extracted this plot. In this plot, the Gaussian unitary ensemble is the one that shows a sharp transition between the ramp and the plateau. The Gaussian orthogonal ensemble is the one that shows a mild transition. And the Gaussian symplectic ensemble displays this weird kink here. So it goes beyond the plateau and then comes back again. So using the same methods, we have repeated the computations, and we have computed the complexity for the Gaussian orthogonal ensemble and the Gaussian symplectic ensemble. And overall, they display the same kind of qualitative regimes. But what is interesting is that the complexity slope demonstrates the difference between the different universality classes. So it is really tied to the quantum chaotic universality class of the system. So in particular, here we see that the left one is the Gaussian orthogonal ensemble, in which the slope goes much softer to the plateau, and the other one is the Gaussian symplectic, in which we see two overshoots. So we overshoot first, and then we again overshoot. So basically this is the one with a more coherent wave function evolution. And now, just to end, let me say that one could be critical and say that this only holds for random matrices and not for realistic black hole models. And to show this is not the case, we can repeat the same steps for SYK. Let me say that SYK is a model of Majorana fermions with a random Hamiltonian, but just including few body interactions. This is the critical thing that differentiates this Hamiltonian from a random Hamiltonian. And the interesting thing is that this for let's say for few body interactions, for particular for 4-body, this is a realistic black hole model that is described at low energies by the Schwarzian theory. So, but we see that the Langsos coefficients behave in the very same manner as before. Only that you see a little bit more ugly plot because you need a bigger Hilbert space to converge, but this is not really, this is expected. And also the quantum complexity also behaves in the same manner and distinguishes. Well, one interesting thing of the SYK is that I didn't put the reference here. Sorry, but this is in the article. So the universality class of the SYK model depends on the specific value of n. So for different values of n, you get Gaussian unitary, Gaussian orthogonal, and Gaussian symplectic. You explore all of them. So here we just took the n's that in order to do a good scaling, we just took the n's that provide the Gaussian unitary ensemble. But you can do the same for other n's, for other values of n and other universality classes. So, okay, at the end, I arrived on time. I was, since the discussion at the beginning of the definition, I began to be a little bit scared. But let me finish the talk with some summary and discussion. So we have provided a Kolmogorov-inspired quantum complexity measure that is non-ambiguous. Its relation to more conventional complexity measures in the quantum complexity is still to be developed, and also to issues like entanglement that they have been asked here, so we haven't done that. But the interesting thing is that it is unambiguous, that it is computable, and that it is a functional of the survival amplitude. So this is very nice from a physics standpoint, because now we can apply it, for example, for the thermal field level. And when we do that, we see that we recontextualize the spectral form factor, which was otherwise a kind of abstract quantity constructed from the spectrum. Now here it is recontextualized as part of a dynamical process involving the thermal field level, and more concretely as the first entry of the probability distribution in the kilo basis. But there is there is an exponentially large other probability distribution, probability entries, no, that form the full probability distribution, and the complexity is going to depend on all of those. So this is a starting point for a bridge between the characterization of phases via partition functions and a novel characterization via complexity dynamics, because as we have seen, well, there is a kind of a involved map, but there is this explicit map between the spectrum of the theory and this dynamical process in the kilo basis. And well, as a question for the future, it will be interesting to further develop the issue of Einstein complexity, and also to develop the connections with the geometry of the black hole interior. That, by the way, as I mentioned at the beginning, we haven't attacked this here, but we have provided like a method to compute the black hole, I mean the wave function of the eternal black hole precisely. And in particular, this should contain all the information required to understand the black hole interior, potentially. So with this, I want to finish, and excuse if I suddenly accelerated the talk and it was not so clear at some points. Thank you.
Any questions?
There's a question that I posted in the chat about the definition of complexity, which maybe if you could look at that one, that would be interesting for me.
So we start in the 0, 0, 0 state, that one.
No, before that, the one that starts with, I think I'm missing some intuition.
Yeah. Okay, wait. Yeah. I think yeah, it's a very good question, and I think I mean, so take into account that so I think our measure will give small complexity to that evolution. I cannot tell you for sure because I will need to compute it. But notice that it's important here that I mean, maybe you say well, this has overlap with all the basis vectors. That's true, but that in a particular basis. But my claim would be that there is this other basis which kind of follows the production of orthogonal vectors as time evolves, in which actually you are going to see that the spread is not so big. It's interesting to these are interesting applications of this formula. But I'm just saying that I would expect that that if you do the calculation, you need to compute for that initial state and for the evolution you are proposing. You need to compute this kilo basis, which is exactly constructed to minimize the spread. And it can be, for example, let me say that one comment is that myself in the past, myself in the past, I did this computation for SYK. So I propose in SYK I propose a very similar definition of complexity, but in the computational basis, which is very similar in spirit to what you are asking. If you do that and compute the spread, which is what I did, you find that the complexity saturates at an exponential value, so saturates at the maximal value, at a time of order the entropy of the system, not exponential in the entropy. So so you see how important is to choose the basis that minimize the spread. So when I choose the kilo basis, I find a complexity that in order to arrive to the maximum, it needs an exponentially large amount of time in the entropy. If I choose another basis, most probably it will give you some very large and not expected value of complexity. But you really have to do this minimization.
Okay, well, I'd be interested in knowing what the answer is if you do that for this particular example. But
We will.
thank you.
We will, and I'll let you know.